Hello everyone, I'm Matthew de Guzman and I'm a computer science major at the University of Florida, and today we're going to be going over the strings and permutation module, specifically the are permutations question. So before we get into the problem, I want to lay out some steps that we have to guide us through these technical interview questions. So I'm just going to write it in this problem first. So the first thing that you're going to want to do before you come up with any solution is really understand the problem. So that can consist of rereading the problem statement multiple times, and looking at the test cases and understanding why the output is the way it is. And in the case of being interviewed, you're going to want to ask your interviewer questions, anything that you have about the problem that may seem murky to you. And in the case of us just being given the question, we can just look at the constraints and understand what that might mean for our solution. So the first step is always to understand the problem. Then the second step is to just come up with any sort of solution. Don't worry about the efficiency, the time complexity of it, because you can always optimize and improve on that later. So just come up with any sort of solution And once you've come up with a solution, you want to just make sure that it's right. So you can go over some test cases and you can jot down your thought process and guide yourself through these examples and make sure that there's nothing that you're missing. And if there is anything that you're missing, ask yourself, okay, how can I improve upon this solution to make sure that it is correct? And then the third step is to optimize the solution. So you might say, okay, well, this is just doing some unnecessary things, so how can I shorten this, maybe optimize the time complexity or the space complexity of it, right? And once you're done with that, if there are any more optimizations after the current optimization, just keep doing that until maybe you've run out of time or you've optimized it as much as you possibly can. So these are some good steps that you should generally follow when you have a problem that you're given. So now that we have these, we can just follow these to try and solve this problem statement. So let's read it first. So in this problem, we're given an array of strings strs such that each string only consists of lowercase letters. And we want to write a method that returns true if all the strings in strs are permutations of each other. So let's look at some sample test cases to really understand what this problem is asking about. So we're given this input array strs, and we're given these three strings, and the output is true. Now the output is true, and we can look at the explanation to see why. It's because each string can be rearranged to match each other. And we look at the first and second string abba, we see that we can just rearrange these first two letters to match this second one. And we can do the same for this one, the second one, and the first one. And we can also do the same for each pair of these strings. So clearly they're all permutations of each other. But now we look at the second example and we see that the output is false. We look at the explanation and we see that abc can't be rearranged to abbc because it only has one b. So it's clear that if one string has like more letters or more characters than the other, then we can't rewrite it. We can't rewrite them as each other because we have to use all the characters. And when you write a permutation, you're never going to increase or decrease the length of the original string. So that might be something to note for the solution. And then we're looking at the third example. These first two strings seem to be permutations of each other. But this last string, however, it includes a letter that none of these first and second strings have. So we can see that the output is false. And then the fourth example, these first three strings look like they're permutations of each other. However, these last two failed to be permutations of these last three. And then for the last string, for the last example, we only have one string in this array. So it's obviously going to be a permutation of itself. And we also see that these strings can be empty. So that might be something to note in our solution as well. And now we can just look at the constraints. So we see that the length of the array is going to be bounded by some constant, 10 to the 4, but it can't be empty. So it always has at least one string, and each word can be empty or have up to 100 characters. And then the last constraint is that each word only consists of lowercase letters. So it seems to be something that we might want to take advantage of in our solution, that each string only consists of lowercase letters, since it was emphasized in the constraints and it's also here in the problem statement. So now that we kind of have this understanding of a problem, it's good to try and just come up with a solution first. And remember, I said you can come up with any brute force solution and we can always just optimize it later. So it seems clear that a good solution here, an easy natural brute force solution, is just to check every single pair of strings in these arrays. So for example, in the first example, we see that abba and bbaa. We want to check if those two are permutations of each other, and then we want to check the first and third, the second and third, and and just those pairs. So that seems like an easy implementation to have. We can just do a brute force solution. So an embedded for loop seems like the way to go. So we're going to iterate through each string in strs, and then we're just going to have another loop. And once we have that, we want to check if these two strings that we're accessing are permutations of each other. And if they're not permutations of each other, then we would just return false. So let's just imagine we have some function called isPermutation. We haven't made it yet, but let's just imagine that we do, and that it returns false when two strings are not permutations of each other. So if we see that we get this function and it returns false, then we can just return false because we found two strings in this array that are not permutations of each other. And if we manage to iterate through all the pairs, all the possible pairs in the strs array, and we didn't find any that were not permutations of each other, then every single string is a permutation of each other and we can return true. So now that we have this solution, we kind of know that it's correct now, and we want to just make this isPermutation method next. So it will return a bool, and we're going to call it isPermutation, and it will take in two strings, s1 and s2. So now that we know what constitutes two strings as being permutations of each other, we want to know how we can implement this condition and check for it. So one thing we can do is check the frequency of each character in s1 and s2. Now, note how at the beginning of the problem it said that each string only consists of lowercase letters. And we know that the lowercase letters, there's only 26 of them from the alphabet. So we don't have to worry about any uppercase letters, numbers, any special characters, just 26 letters. So from that, we can say, okay, let's say A is abc, right? And then the second string is cba, right? We'd check A appears once in s1, B appears once, and so does C. And we check the same thing again for s2, and we see that it has the same frequency. Okay, so we know that these are both permutations of each other, and we'd check because the frequency of A, B, and C are all the same. So one thing we can do is take advantage of the ASCII code, which maps each character to some number, right? And in this case, the lowercase letters, it starts from A, is mapped to 97, and then B is just 98, and then it goes all the way up to Z, which is just 97 plus 25, since there's 25 other letters after A. So one thing we can do is access a vector or an array of 26 elements and take advantage of this ASCII code and assign each element an individual index in that array. So now that we know what the index of each letter is, we're accessing the frequency, and we can just change it every time we encounter a certain character in S1. Now another way to do this would be with hash maps, but we haven't gone over hash maps yet, so we're just going to do this ASCII code and vector implementation. So we've gone over how to check if two strings are permutations of each other and how to map their frequencies. So we're just going to want to check if each character has the same frequency, and in this case we're just checking if all the values at each index are the same. And if they are, then each character has the same frequency in S1 and S2, and they're both permutations of each other. And if they're not, then it doesn't satisfy this condition that we said, and these strings are not permutations of each other, so we return false. So now that we have this sort of implementation in our head, we can just kind of write it out. So we said we were going to make a vector, and it's going to be a vector of ints. And let's call this one just S1 map. And it's going to have 26 elements since, like we said, it's only the lowercase alphabet letters. And we're going to have another vector called S2 map. And again, this is just to map each character in the strings to some frequency. So next we're going to iterate through both of the strings. First we're going to go over S1, and then we're going to say, okay, S1 map, and we're going to get the index of that character, so int c, and then -97, since that's where the first letter starts. And then we're just going to increment it once, since we've now encountered it in S1. And we're going to do the same for S2, so char S2, and then access that via the ASCII code, and then just increment it. So now what we've done is map frequencies of characters in S1 and S2. So that's what we've done with these two for loops. Now what we want to do lastly is just check if the strings now have the same frequencies. So check if same frequency. So we're just going to iterate through each index dot size. And remember, each index is representative of some character. So we're just checking if these characters are mapped to the same frequency. And if we find two that aren't mapped to the same frequency, then we want to return false. So what we're going to want to do is say S1 map I to check the frequency of the character mapped at I. And then we're going to want to say if that's not equal to the frequency mapped in S2, well then they don't have the same frequency of the characters, so we just return false and they're not permutations. However, if we'd never found two frequencies that are unequal, then we do have a permutation, so we just return true. Now let's just run through some example here in example 1 to see if our isPermutation method really works. So we have this first string bbaa and this second string bbaa. And we want to see if our algorithm says these are the same permutations, or not the same permutations, but they are permutations of each other. So we iterate through this string S1, and we're just going to say bbaa is S1. So we see A first, and we're going to say that A has a frequency of 1. Then we see B next, and we're going to say B has a frequency of 1. And then we encounter B again, and then we update it to say it's 2. And we encounter A at the last index of the S1. And so we update it again to say 2. Now we iterate through the next string bbaa, and we see that we access B twice, so B has a frequency of 2. And then we access A again twice, and so we say A has a frequency of 2. And the rest of the characters in the alphabet, so C all the way through Z, just have frequencies of 0. And then we'd go through each of these frequency maps, and we say, okay, A has 2 appearances in S2 and 2 appearances in S1, and B also has 2 appearances in S2 and in S1. So we see that these are both permutations of each other. And we see that this also works for the case where they're not permutations of each other, because A shows up once in this string in example 2, but B only shows up once, whereas B shows up twice. So then when we're checking these frequencies, we see, okay, B appears once, B appears twice, so we know that they're not permutations, and we just return false. So it seems clear that this isPermutation method really does work, and that it does check if two strings are permutations of each other. And now that we've done that, well, now we know our permutations method really works, since that was just the last thing that we wanted to do with it. And so yeah, let's just go through one example again, just to really make sure it works. So abba is where we start with I equals 0, and then j is equal to 0, so we're accessing the elements again. And it seems pretty clear that each string is going to be a permutation of itself, and it's true because it's going to have the same frequency as itself. And then we go on to this next string, and we compare abba to bbaa. And we already checked before in our previous example, and we know that these are the same, or there are permutations of each other. And then we go to the last string, two a's, two b's, they're permutations of each other. And then we basically just do the same thing again with bbaa and abba. They have the same frequency. Now we check with itself, and it's a permutation, and then we check with the string ahead, it's a permutation, and then we go again once more to aabb, and we compare it to all the elements in the array, and we know that they're all permutations of each other. So it seems like this algorithm, although it may not be the most efficient, it does seem to work. So now let's just test our code against the rest of the test cases and see if our code actually works. Okay, and there you go. All test cases passed. So we see that this test case does work. Now the one thing we're also going to want to do is just check the time complexity. That is a good skill to have, as it may come up with in your interview, and it will allow you to sort of see how you can make your algorithm more efficient. So we see within this code we do have these embedded for loops, and let's just say that the size of n, or the size of strs, we just call that n, right? So we're doing n iterations already, and within each of those n iterations we're doing another n iterations. So it seems as if this algorithm is at least O of n squared, and it just depends on whatever or what the time complexity of this is permutation method is. So before we can determine the time complexity of this R permutations method, we should check what the time complexity of the is permutation method is first. So we see that with the is permutation method, we're given these two strings, s1 and s2. And let's just go over what we actually do in this algorithm. So first, we just initialize two vectors of length 26. We see that that doesn't change with respect to the sizes of s1 and s2. So those are just constant operations. However, next, we iterate through both of these strings, s1 and s2. So it seems as if these for loops are variable and subject to change, and they're tied down to the lengths of s1 and s2. And after these for loops, we just do another constant loop size iterating through these 26 elements. So the only thing that really happens here, that is in this algorithm, that is dependent on the sizes, the input of s1 and s2, are these for loops. Now we're only doing one iteration through each s1 and s2. So let's just call the length of the largest string m, right? So it seems clear that the time complexity of this would just be O of m, since we iterate through the largest array, or through the largest string. Now let's say, okay, s1 and s2 both have the same length, right? Well then this would just be O of 2m, but from the properties of time complexity, we know that that is also just O of m. So if they're not equal size, then it's always just going to be some constant less than 2 times m, which is always just going to be O of m. And if they are equal size, well then it's, like we said, it's just going to be O of m. So the time complexity of this solution just relies on the largest string, which is O of m. So now that we know that within this R permutations method, the innermost loop does an O of m operation with each iteration. So we can see that this entire for loop is an O of n times m operation, where n is just the size of strs. And seeing that, we now know that with each iteration of this outer for loop, we do n iterations of an O of n times m operation. So it's clear that this entire for loop is just n times the time complexity of the inner loop, so n times m, which is just O of m times n squared. So we see that this is already quadratic in terms of n. And after this for loop, we don't really do anything else. We just return true, which is just a constant operation. So the entire time complexity of this solution is just O of m times n squared. So that doesn't seem to be the best, it doesn't seem to be the most efficient algorithm, at least, just because it does seem to grow a lot larger when n gets larger. And you also might have noticed that we were doing some unnecessary calculations within these for loops, as we'd already checked if two strings are permutations of each other. Now, before we go on to optimizing this solution, we can just take a look at the space complexity as well. And we see that this algorithm doesn't really allocate any space to accommodate, or that grows with the size of strs. And we look at the isPermutation method, and it does allocate these S1 and S2 maps. However, those are just constant sizes and don't have to do with S1 and S2 at all. So this is just an O of 1 space complexity, and so is the rPermutations method. So it's at least efficient in terms of space, as we can do this without allocating any extra space. Now, let's look at how we can make this algorithm more efficient, if it's even possible, right? As that was the last step in our solving this problem, optimize the solution. So we looked at this first solution and we saw, okay, abba, bbaa, and aabb. We see these three strings, right? Well, look at these last two strings, bbaa and aabb. They're both permutations of each other, and they're also both permutations of abba. So you might want to say, okay, these two strings are both permutations of one string. Could they be permutations of each other? Well, from our isPermutation method, the condition we came up with for two strings being permutations of each other certainly allows that statement to be true. We see that bbaa has the same frequency as abba, and so does aabb. So it seems clear that since these two strings have the same frequency of characters as one string, they have to have the same characters as each other. So we can kind of say that these are both permutations of each other without even having to check. And you can say that for any number of strings, right? Let's say we had 10 strings and they all had the same frequency of characters as one string. Then we know that they're all permutations of each other, since they all have the same frequency of characters as each other. And so you might be able to see how we can sort of take advantage of that in our rPermutations method. And we can compare every other string in strs to the first string. And if we find that all these strings in strs have the same frequency of characters and are permutations of the first string, then we know that they're all permutations of each other. And if we find one string that's not a permutation of the first string, well, then we know that not all strings have permutations of each other, as we just found a pair that aren't permutations of each other, and we can just return false. So we can get rid of this inner for loop, and instead of comparing the ith string to j, we just compare it to the first one, and we can just start this at 1. Now, the isPermutation method doesn't have to change at all, so it seems that we already have our solution. And let's just go through one example. So let's go again from the first example. We have the string bbaa, and we want to check it against the first string. We see that these both have the same frequencies, so they're permutations of each other. And then we check the last string, and it also has the same frequency as the first string. And so our algorithm finishes and we just return true, which is certainly the output here. And now we can go to something like the third example. This second string has the same frequency of characters and it's a permutation of the first string. Now we go to the last string, however, and it's not a permutation of the first string, so it returns false. So it seems as if this solution is correct. And before we test it, let's just look at the time complexity and see if this is an actual improvement. So we can see here that we are doing about n operations, or n iterations, and within each iteration we're doing an O of m operation. So this whole for loop is just O of n times m. And once we finish the for loop, well, that's all our algorithm is, just this one for loop, and then we just do one constant operation. So O of n times n is significantly better than our previous time complexity of O of m times n squared. This is now linear in terms of n, while the other one was quadratic. So the efficiency is definitely there. Now let's just check if it also works against any other of the rest of the test cases. And there you go, okay. So we see that this solution does in fact work against all the other test cases, and the time and also the space complexity is the same since we're not allocating any more space. And what I want you to take away from this example is not necessarily how to check if strings are permutations of each other. It's how I came up with the solution and how we were able to walk through it by following these 3 steps. So first, remember, we tried to understand the problem. So we looked through this problem statement, and then we just looked through each of these examples, and we looked at the constraints. And we came up with a solution that took advantage, or that was just brute force, right? We didn't care about the efficiency of it. So we just came up with a solution first, and we saw that it worked. And we also broke the problem down into some subproblems. And that can help sometimes. Instead of just dealing with everything at once, we said, okay, just imagine we have this method that takes care of checking if 2 strings are permutations, and then we can go into that. So really just dissecting the problem and not necessarily worrying about making it as efficient as possible allowed us to come up with a solution first. And then once we finished the solution, we looked at the time complexity and space complexity, and we looked at the problem again and said, okay, was there anything else we could take advantage of to optimize the solution? And there was. We took advantage of this sort of transitive notion of these permutations, and we were able to lower the time complexity to n times m and get a more efficient solution. And so that's all I really just want to emphasize in this video, and that's it. We came up with a solution. Thank you for watching, and have a nice day.